Me dices, Rosa, si lo puedes ver.
Sí, perfectamente.
Ya, aquí yo no veo a nadie, así que tú me avisas si alguien quiere dar una charla. Okay, so today I'm going to talk to you a little bit about cosmic alchemy in the era of gravitational wave astronomy. Again, I think a lot of the work that I've been doing in this field has been in collaboration with a lot of people. You can see there many people that are not in the cold too. In particular, I think William Lee and I, I learned a lot from him when I was a grad student on the field, and he sort of was the first one that got me excited about neutron star mergers. So he deserves all the blame for any mistake I make and any success that we have had. Okay, so I'm going to try to give you an overview of the nuclear properties and the R process in general. Hopefully it'll be pedagogical. If you feel that it's not pedagogical enough, just please stop me and we'll discuss in a little bit more detail. Then I'll tell you a little bit about what we know from the R process from abundance observations in stars. So what can we decodify from doing high resolution spectra of those stars? Then I'll tell you a little bit about neutron star mergers as sites of R process nucleosynthesis, and really focusing on the observational signatures. And of course, as you know, we were incredibly lucky to detect the neutron star merger and the ensuing electromagnetic radiation. So I'll talk a little bit about what we learned and what we were expecting and what we learned. Okay, so for astronomers, as you know, this is our periodic table, and there's a huge amount of information in this plot of mass number versus abundance. So the first thing that you notice is that the abundance peaks, something that we'll talk a little bit more about is the uneven distribution, why you see those up and down variations. But the thing that is incredibly evident right now is that the peaks coincide with nuclear structure, in particular with closed protons and neutron shells, which you can see there, which are usually referred to as the magic numbers in nuclear physics. Something important to highlight is, of course, that iron, which, as we know, is the most bound nuclei in the universe, has basically has basically closed shells and neutron shells that coincide, and it's the highest mass number nuclei with equal number of neutrons and protons. And then as you go to heavier and heavier elements, what you realize is that the number of neutrons starts exceeding that of protons. And you go, for example, to lead. And Rosa, I don't know if you can see my cursor if I point.
Yep.
Yep. But if you look at lead, for example, it has two magic numbers, 82 and 126, and it has a significant fraction of neutrons. No? So we're going to talk a little bit about stability of nuclei and how basically the abundance pattern actually relates to these closed neutron and proton shells. So what I'm going to talk about today quite a bit is the other peaks that you see there that naively, they don't seem to actually follow neutron and proton closed shells, but I will argue otherwise. Another important thing to realize is, of course, that nuclei that are heavier than iron are almost exclusively made by neutron capture. So as you know, there's two impediments really to make elements that are heavier than iron. One is, of course, that the Coulomb barrier increases with C, so it makes it progressively more difficult to have any charge reactions, particularly at the temperatures that are in the interior of stars, and that's a big impediment. And the other impediment is, of course, that, as you know, since iron is the most bound nuclei, if you want to make nuclei that are heavier, you have to give energy to the system. So the reactions are no longer exothermic, but they're endothermic. So almost exclusively, elements beyond iron are made by the neutron capture process. And astronomers, as you know, we're not very innovative in our names, and we call the S process as slow and R process as rapid. So what does that mean? When you capture a neutron, you beta decay. So if the capture rate of neutrons is slower than the beta decay, you basically move very close to beta stability, and that's basically where the S process is made. Very, very close to stability, you capture a neutron, you beta decay, and so forth, and you start building heavier and heavier nuclei. And then the rapid process, the R process, Therefore, you have to capture neutrons at a much faster rate than the beta decay. So of course, the timescales there are very, very short. And then I'm showing you there here the S process and R process in the sun, which is going to become central to the conversation that we're going to have. And then I really want you to think about these. In the R process, we have first, second, and third peak. And in the S process, we have first, second, and third peak. And I'll talk a little bit about where those three peaks arise from. So I'm going to devote a little bit of time into explaining this plot. This is from the classical review of Chris Newton. So what you're seeing there is you see the number of protons in this axis, the number of neutrons in this axis. I'm just going to highlight that if you capture a neutron and you beta decay, you move in this direction in this plane. So that's an important thing to capture. The first thing I want to talk about in this diagram is the black points. So this is basically the stable nuclei. So if you are moving in the S process, if you're basically capturing neutrons at a much slower rate, then you are always moving very, very close to the stability, what we call the beta stability line. Okay, this is where stable nuclei lived. If you, for example, pick the stable nuclei and start going down such that you're decreasing the number of protons, the nuclei become unstable, progressively more and more unstable. And what you see here is the time scales for the beta decay, which could be tens of milliseconds once you get to the red component. So something that it's incredibly important to realize is that if you want to make the R process, this is an R process pathway with separation energies of a few MeV, you have to capture these neutrons very, very far from stability. Okay, so the conclusion, which is natural just from looking at this plot, is that you have to have capture rates that are faster than tens of milliseconds. And then you say, well, what object in the universe has a dynamical time scale that it's of order of milliseconds? Well, a neutron star. Once you go to the next more compact object, a white dwarf, then the timescales are just way too long. And therefore, the R process has always been assigned to either when a neutron star is formed or when two neutron stars merge. Yeah. Okay, something that I'm going to spend quite a bit of time talking to you is these closed neutron shells, these magic numbers. This is very, very important. So what happens there in these closed neutron shells? So of course, if you think about it from a perspective of nuclear stability, those nuclei are incredibly stable. So they don't want to capture neutrons, no? And that's essential. So what I'm showing you here is the neutron capture cross-section of nuclei in the S process pathway. So this is, again, it's happening at smaller energies of the S process, but there's a few aspects. I think this is, of course, Clayton is a textbook, and what you see is the cross section, the capture cross sections of neutrons. So the first thing that you actually notice is that there's an odd, that odd mass numbers tend to have higher cross sections than even nuclei. So you see the wiggles that you saw in the abundance pattern also represent here in the cross sections. But the thing that it's incredibly dramatic is how deep, and how intense is the decrease in the neutron capture cross sections at the magic numbers. And that makes perfect sense because those nuclei are basically stable. They don't want to capture neutrons, so the cross section drastically decreases. Okay, and then the way that I want you to sort of envision these neutron capture rate is, imagine that you have a flow of neutrons. And as soon as you get to these magic numbers, there's a stagnation of the flow. The flow cannot proceed at the same rate, and therefore you get accumulation of neutrons at those particular areas. And as a result, abundances anti-correlate with neutron capture cross sections. So that immediately gives you a sense like, oh, that makes sense. When those magic numbers were present, I saw the drastic enhancement of the abundances. Another analogy is imagine that you're driving cars in El Periférico, there's an accident, and then there's basically a bottleneck and a pile-up, and that pile-up, leads to higher abundances. So we're going to talk about, these magic numbers, particularly the neutron magic numbers, and 50, 82, and 126. And those are related to what we call the first peak, the second peak, and the third peak of the abundance pattern. Okay, so let's just get ourselves oriented in this plane. So imagine that you are doing S process capture. So I'm moving here close to stability. I see this magic number. I stagnate here, so I'm going to have my first peak here. I continue my second peak here, and I continue my third peak here. But then what happens for the R process? So the R process is captured really far from stability. So I basically capture my, cross my first magic number here. So I get a first peak here, a second peak here, and a third peak here. But those nuclei are unstable, so therefore I beta decay. So the way that you can think about it is that this third, second, and first peak shift to the left just because these neutron numbers are actually achieved, but they're really, really far from stability. And by the time they decay, those neutron numbers are eradicated because they've got transformed into protons. So this is basically what's happening. Is not that current, there's nothing really too magical that happened. It's just that the R process was made far from stability, and by the time you beta decay, you have your third peak, it's moved to the left from the S process. Your second peak is moved to the left, and your first peak is moved to the left. So in mass number, you see these first peak, second and peak, and third peak. And at first sight, they don't seem to correlate with nuclear structure, but they do. It's just that they correlated for nuclei that were not stable at the time. That's when you cross a magic number. And that gives you a sense of really trying to understand the abundance pattern. Okay, I'm sorry, I just got a call. So this is basically...
Sorry, Enrico?
Yeah?
Now that you're then explaining that previous slide, so I've never really understood. So what are the horizontal and vertical black lines? What do they represent?
These ones?
Yeah.
Yeah, these are the close neutron and proton shells. So those are the ones where the nuclei are stable. So that's the number of neutrons, that you need for a closed shell in the nuclear model. And that basically tells you what are the, what is the stability of nuclei. So what I was just trying to highlight is, imagine that you are, you're a neutron and you want to be captured, but you're in a nuclei who basically has, all of its neutrons, and therefore the shell is closed in some ways. So it's highly stable. Those particular neutrons are going to have a really hard time to be captured there. Does that make sense?
Yeah, yeah.
Yeah, so this is basically related to nuclear structure, no? And
Vale. Okay.
And so you have protons, in this direction, and neutrons, vertical in the other direction. So horizontal protons, vertical neutrons.
Vale, thanks.
Okay, so here you kind of see the pattern shifted to the left. No, you have, the first peak here, the second peak, and the third peak. And I just want to highlight a few things. One is that one important thing is that a particular element can be made by both processes. You can see here lead, for example, which is doubly magical, has a contribution from the R process, but it's primarily made by the S process. My favorite peak of the R process, which is the third peak, is platinum and gold. So especially coming from the Mesoamerica culture, that's of course our favorite peak where gold stays. Another important thing here is europium. Europium is in a rare air peak. I won't have time to discuss this, but in some ways this is strange because it's between the second and third peak. So what's going on here? Is it related to nuclear stability or not? And we can talk more about that. But there's a significant amount of debate in the nuclear physics community about how you get this peak. However, europium is primarily made by the R process, and europium has a very strong oscillation strength line, atomic line, which creates a feature in the spectra. So we use europium in the spectra of stars because it's the most prominent line to see how much R process a star has. Barium, for example, and strontium are used to think about the S process. Okay, so what do we know about stars in general for the R process? So this is kind of, if you like gold, of things that are very highly enriched with gold, this should be your favorite star. This is called the Sneeden star because Sneeden discovered it. But this star is actually a low metallicity star, but it has its relative proportion of our process, and therefore gold is incredibly high. But it looks like, at first sight, like a very normal star. So what have we learned? So these are a sample of low metallicity stars. So these are the stars that were produced when the Milky Way was in its early infancy. And what you see superimposed there is our process abundance pattern from the sun. And the thing that is incredible, that they have been shifted arbitrarily in normalization. So the thing to know is that, yes, there's variations from star to star about the total amount of our process material that they have, but the abundance pattern is extremely robust. And that tells you that whatever is making the R process has been operating in an incredibly controlled way, and it's produced a very, very robust pattern. So in some ways that it's not as sensitive, or should not be that sensitive to the initial conditions, and it's been operating like that since the early universe. And this is particularly important for the second and third peak. So what we call the heavy R process, we now know observationally that it's been extremely robust, and the ratio of element to element is incredibly robust. The normalization can change, which is the total amount of mass. So for example, I'm going to show you this Newton star, which is here. So this is europium abundance. As you know, in astronomy, we use abundance in logarithmic scale. So this basically has almost 100 times more gold relative to iron than the sun. So it's highly, highly enhanced in our process. I think I'm going to show you these two stars so that you can see their spectra. Something also that it's incredibly important is that only a very small fraction of metal poor stars show our process signatures. And another thing that it's incredibly important is the drastic changes in our process contents, the RMS fluctuations. Is there a question? No? Bueno. So you can find two stars at low metallicity that have changes in abundance by almost a factor of 1,000. And I'll talk a little bit about that in a second. But here I want to show you these two stars. So for example, if you look at the calcium lines here, they're very, very similar in their abundance process. But if you actually go and look at the europium line, which is here, look at the difference between the blue and the red. So huge difference in the content of europium of this star. So this is this Newton star, and this is one of the lowest europium or R process relative content. So to give you some intuition, if you want to produce the total R process in the Milky Way, the rate of formation, so just for those of you that may not know astronomy as well, or the evolution of the Milky Way, the Milky Way is forming about 1 solar mass per year, about 1 sun per year. And of course, multiply that by the age of the universe, it gives you more or less the total stellar mass of the Milky Way. So with that in mind, the total amount of our process that you have to produce is about 10 to the minus 7 solar masses per year. Okay, so that's a very important number to have in mind. So if I multiply that by the age of the universe, say 10 to the 10 years, I get about 10 to the 4 solar masses of our process. So in the entire Milky Way, locked up in stars and gas, there should be about 10,000 solar masses of our process. And then when people contrasted these two formation mechanisms, a wind in a core collapse supernova just after the neutron star is formed, that happens about once every 100 years. So it's 10 to the minus 2 per year. So then the requirement in this model is that you have to produce about 10 to the minus 5 solar masses per year. While in the case of neutron star mergers, they happen once every 10 to the 5 years. So then it's 10 to the minus 5 per year. And then you need a production rate that is about 10 to the minus 2 solar masses per year. So you multiply these two, and then you get the magic 10 to the minus 7 solar masses per year. So the way that you should think about this is that neutron star mergers are rare but produce a lot of our process, and core collapse supernova are much more common and are thought to produce much less. And that's what people were contrasting. So I'm going to try to tell you a little bit observationally, what do we know about the rate production of this. So there's a very simple argument that you can make, which is actually quite nice. So if you have an explosion, and it doesn't matter if it's a neutron star merger or a supernova, what ends up happening is you have a blast wave the blast wave starts expanding. It's incredibly hot, and it has to sweep enough material to start cooling. And that's usually what it's called, the cooling mass. And it's basically derived here. No, so the cooling mass, of course, depends on metallicity, because if you have more metals, you cool more efficiently. It depends on the explosion energy, because it tells you how much energy you ultimately have to cool, and the same with the number of particles. No, if you're denser, then it's, you basically are much more effective at cooling. So if you think about it, you say, well, if I take a neutron star merger, what is the fastest that I can turn that gas into stars? And the argument is the cooling mass. So before the material cools, you cannot turn it into stars. So this is kind of, it gives you a limit of how much material I have to basically input within a cooling mass to produce the observations that I see. So the argument is as follows. You say, well, within a cooling mass, I know how much hydrogen I have actually swept. And in the abundance of stars, I know how much europium to hydrogen I have to actually produce in order to explain the abundance of that star. And that gives me a minimum mass of our process. So it's a very elegant, very simple argument that you can make. And this is what you derive. So you basically turn the europium over iron abundances, which are plotted here, you put them into a minimum mass. And then you realize that one of these events, particularly if these stars are produced by one event or so, require at least, in the most highly enriched, which is this Needham star, requires a mass of about 10 to the minus 3 solar masses. Well, of course, the constraints of core collapse supernova are here, which we talked about, which is of the order of about 10 to the minus 5 solar masses. So this immediately rules out standard supernova as a way to enrich these stars. And the natural conclusion, I think, that now everyone believes is that the production of heavy R process elements need to operate robustly, as we talked about, because the abundances pattern is so incredibly the same across the star. And they have to happen at a drastically reduced rate when compared to core collapse supernova. Okay? So that's basically the paradigm. So either they happen in neutron star mergers, or they happen in a very rare supernovae. Maybe one supernova out of 1,000 or so can make the R process. So then the question is, what's special about those supernova? And that's sort of the debate that is currently going on in the field. Okay, so for neutron star mergers, I'm going to show you very simply how this is basically made. So I'm going to show you one of the early simulations Stefan Rosgo performed when we worked together, and I was a PhD student. Oops. I'll play. Let me know if you don't see it. So these are two equal mass neutron stars. Again, no GR yet. You get, mass shredding in the outer Lagrangian points. This is the sort of calculations that William Lee sort of pioneered in the field. And what we're basically looking at is the tidal tails, the amount of the little material here that is actually able to go above the escape velocity and escape. And this is an incredibly robust, relatively simple problem because it's not irradiated by neutrinos. So I'm just going to focus on the tidal. This is called the tidal tails. So I'm going to show you a movie, and I'm going to stop it here. Okay. So again, we spent quite a bit of time looking at that diagram, so now we see it in real time. So this is proton number, neutron number, and what you're going to see here is the abundances. Now, at time equals 0, and then I can highlight a few things. The temperature here goes in red, the density as the material expands goes in blue, and the heating rate, which is the amount of energy deposit, goes in black. So the first thing that you should notice is that at time equals 0, the material is so neutron rich that you have tons and tons of neutrons, but in nuclear statistical equilibrium, you also have heavy nuclei. So you already have the neutrons and the targets. And that basically happens at very, very, when the material is very, very neutron rich. So this is what is going to happen is that all of these initial seeds in nuclear statistical equilibrium are going to capture neutrons, and you're going to see it now. Oops. In real time, if I'm able to press play. Okay. So there you go. So you capture neutrons. You can kind of see the stagnation in the magic numbers, the first, second, and third, and then you start decaying back to stability. And then you clearly see, the first, second, and third peak, how it's basically shifted to the left. Yeah, and of course, there's a lot of heavy nuclei that you make that are incredibly unstable, and we don't see today. And you do that with a nuclear network, and this is one of the first calculations.
Érico,
Ajá.
¿de dónde llegan los heavy nuclei que están presentes al principio?
Estos vienen de, o sea, si tú agarras y pones nuclear statistical equilibrium, en equilibrio, you already get those nuclei. O sea, esos ya existen como función de la distribución en equilibrio de esas condiciones iniciales de entropía y densidad.
Ok, gracias.
Yeah. Okay, so something important that I wanted to highlight is the heating rate. So as material is expanding, then there's a significant amount of heating that comes into the material, and that's actually what's going to power the electromagnetic radiation. And so this is what I'm showing you here is one of the first calculations done in this nuclear network by Luke Roberts, who worked in his PhD with me and William. Okay, so just for fun, if you think about how much material is produced in one of these events, and of course I'm obsessed with gold, so let's talk about gold. How much gold you produce in one of these events is about a Jupiter mass of gold. And then if that's hard to kind of put into context, well, this is more or less the amount of gold stored in about 1 million stars. So one of these events can actually supply a lot of stars with gold. I'm going to make a very quick analogy, which I like, that it's imagine that you're enriching the universe and you do it with supernovae, with gold. You do it with supernova. So supernova happen very frequently, but they produce a little, very little amount of gold. So my analogy there is like a chocolate cookie where the chocolate is very thin and distributed, very homogeneous in the cookie, while neutron star mergers are like chocolate chip cookies where all the gold in our process is very highly concentrated. So therefore, if you're a star in the early universe and are born from gas close to the chocolate chip, you will have a lot of our process, while if you're far away from the chocolate chip cookie, and that's why we believe that you see these large fluctuations. Is there a question? I felt no. Okay, so if you think about the evolution of neutron star mergers, as you know, they span giga years or so, hundreds of millions of years going around each other. They basically lose energy and angular momentum through gravitational waves. They become progressively closer to each other. Then they become dynamically unstable, and I'm just discussing right now the unbound material. The unbound material basically expands very, very quickly, few milliseconds. So again, timescales that are quickly enough to produce enough neutron capture. And then ultimately, the only thing that matters is how much mass is ejected and what is its velocity. And its velocity is basically related to the escape velocity at the outer Lagrangian points. What it's interesting is that this flow is expanding, but there's a lot of decay. Both particles and photons are decaying into this material, but it's optically thick. So all that energy is being captured. It's fighting adiabatic cooling from this expansion, and it keeps the material hot. And this is where we actually think that that's what's powered the electromagnetic transient. And then you have to wait about the size of our solar system or so, expansion of about a few days, so that the material becomes optically thin, and then you start seeing the photons. So that was kind of the expectations we had. Again, this is the paper by Luke Roberts. When you are following it, and you use the same formalism for supernova. This is the classical Arnett, where you have basically your energy, you have your adiabatic cooling. So that's basically expansion is draining internal energy out of the system. Radiation is also negative, and it's draining radiation on a diffusion timescale. So the photons are leaking out, but the key is basically the heating rate. What is the heating rate that keeps? And something that we found out in this paper was basically that it was a power law. And therefore, you expect the total bolometric luminosity of this event to be that power law. And then look here in the paper, actually show basically the contribution of one nuclei, and that you can see that at a particular time, there's many, many nuclei decaying as a power law, decaying at a particular instance, and the sum of all of that is a power law. So, there's basically many, many elements contributed to this decay, and you get, something that is close to T to the minus 1 in decay. So if you're not familiar, yeah.
I got a question. So so this is related with the nuclei that is being produced via our process, or is more due to the decay back to stability due to the beta minus, beta plus decays?
Yeah,
I'm sorry.
No, yeah, you're right. It's a mixture between, the back to stability and also fission. So a lot of these elements are actually
All right.
Fission themselves. So then the fission fragments also start producing heat. So yes, you're right. It's
So
basically.
So in terms of that, which would be the most, say, important rates that we have to know in order to sort of get the right signature of this signal, so to say? So which are the most important rates that we have to know in terms of these scales?
I'll tell you a little bit more about that. I mean, one of the problems is that it's hard to identify a particular nuclei. So we're trying to work hard, particularly at late times, we think like californium, for example, nuclei that at late times may actually contribute with significant fraction of the heat. But because there's so many nuclei, as you can see there, there's, kind of getting the isolation of one is not clear. I think the work that we're trying to do now is trying to say, well, did we produce first, second, and third peak? And what is the contribution of each of the peaks? And then try to basically, from the luminosity, backtrack the abundance, if that makes sense. So more as groups rather than individual elements. But you're right. I think, if you do the accounting, the problem is that one particular nuclei do not contribute with significant fraction of the total luminosity, but at a particular time. And in some ways, this is, Liam Paczynski in '98 kind of predicted that this was going to be a power law because of that. So let me show you an analogy of this. Maybe this will be exciting to you. So this is actually how the Earth is actually heated. What the internal heat of the Earth comes from these radioactivity of these nuclei. And you can see this is basically when the Earth was very young, aluminium-26 was basically contribute with the majority of the heat. But today is really potassium and uranium and thorium. And these two elements are actually our process elements. So for example, in a recent paper that we wrote, we said that, if you have two solar systems with with a fraction of 2 difference in europium and thorium, the magnetic field that may be produced in Earth will be very different because the dynamo will operate at a different rate just because the convection inside the Earth will be different. But this also gives you, as you were saying, I think we're used to think about these sort of plot when we think about decay, but in the particular case of the R process, you have so many unstable nuclei that it's a little bit harder to identify, the contributions of each of them. But this is kind of this is a nice analogy of what's happening inside the Earth. And the hierarchy, as you were saying, So what you were asking is like, oh, please give me the hierarchy. So if I can look at a particular time, I know which of those nuclei are contributing the most. But it's much harder to do than in the solar system. Okay, so if you try to power a light curve, this is work that I did in collaboration with Dan Case. And if you have a type 1a, which is primarily powered by nickel to cobalt to iron decay, you get these light curves. The bolometric luminosity follows the decay rate. And in these kilonova models, which were named because they were about 1,000 times brighter than nova, you can kind of see this is the bolometric decay. And the idea is that the light curve, should more or less follow the bolometric decay. Now, one of the promises, of course, these objects have less mass, and therefore they're not as bright. As you can see, there's almost 2 orders of magnitude in brightness, and they also peak and decay relatively quickly. Okay, so I wanted to just give you at the end like some idea of some of the uncertainties that we have. So if you're thinking about opacity now of photons, so those photons have to leak through these nuclei, but these nuclei have electrons. And when you think about electron, kind of complexity, is really not the number of electrons that matter, is the number of, available valence spaces that matter. So F-shell atoms that live here, which are the lanthanines and actinides, have basically a very, very large degrees of freedom in the way that you can arrange the valence electrons. And therefore, they have very, very large number of lines. So the opacity, particularly in the optical and in the infrared here, is very high. Why, for example, iron, which is in a supernova, it's more of a D shell. And even though the opacity is large, the level of complexity here, the number of available permutations in which you can put these valence electrons is much smaller. No? So I'm going to give you, for example, this is kind of pioneer work that Dan Kaysen did in trying to think about, can I basically think about how, statistically, what is the opacity of nuclei or, that are lanthanide versus D shells. So this is, for example, iron is here versus something that has F shells. And what you can see is that the opacity is significantly higher. What does that mean is that you have so many more lines. Here you have hundreds of millions of lines, and here you may have hundreds of thousands of lines. So therefore, if you have lanthanide, the opacity all the way into the infrared is going to be very high. So these transients are going to be red, rather than basically picking in the optical. And that was one of the predictions that he made in advance of the observations, that you have to be worried about the complexity of these atomic structure model. Okay, so these were sort of predictions that were made in advance of the observations. If you have very few lanthanide, and they leave basically between the second and third peak. So if you have no heavy R process, then these will be very small. And as you can see, you can get a transient that peaks in the optical because the number of lines is much easier. You can escape. And the more heavy R process you put, the redder the spectrum becomes. The opacity drastically increases. So that was basically a prediction made in advance of the observations, that if we saw material that was extremely reddened, then we know that certainly second and third peak had to be produced. Another important thing that you can get from the observations is actually the ejecta velocity, because these lines are actually spread kinematically. So you can kind of see that the width of these features increase as a function of velocity. So you can also, even just by doing a cross correlation in the spectrum, you can get the size of this width, and it tells you more or less what the expansion velocity is. So that's another attribute. I want to highlight something important, that we don't really know all of the oscillation strengths, all of the line energies, all of the probabilities of these lines. We don't know from first principles. They can be calculated, but they're expensive to calculate. So these models that Dan Kaysen has built, rely on a statistical description and saying, what is the distribution of oscillation strengths, what is the distribution of energies, and how many lines on average there are. And then you construct this spectrum that way. And again, going back to that question, some of these features are not single element features. They're basically agglomerates of many, many lines. So that makes it a little bit hard to know. So of course, we go back to, an incredible day, August 17, 2017. I don't have to tell to this audience how incredible that day was. And we were, I in particular were incredibly grateful that I was participating in the 1 meter to hemisphere group led by Ryan Foley at UC Santa Cruz, where we have, Lick Observatory at 1 meter and the SWOPE telescope. And this is our team. Most of you know Ariadna. This is Ryan Foley, and you can clearly see that I'm the oldest of the group. And we were incredibly lucky to be the first one that detected this radiation. And it was really thanks to David Coulter's algorithm development in how we sorted the galaxies that we were looking at. So we got lucky. We were the first team to see the light. But something that you can clearly see is that the object started to be very blue and then turned very red. Very similar to the predictions that we had. So the argument is, there was basically not a lot of opacity early on, and then the opacity was built up as a function of time. I know I'm running a little bit out of time, but there's lots of exciting things that you can do with this event. But in particular, I just wanted to highlight: are we sure that we have actually produced these heavy elements? So the first thing is, we talked about the bolometric luminosity being important. So this is the heating rate predicted by Look. This is trying to reconstruct the bolometric luminosity, and we do a relatively good job early on in producing the total amount of energy. The minimum amount of mass that you need to produce is about 0.02 solar masses. And then at late times, it becomes complicated because the efficiency of thermalization and the fact that the particles are actually leaving without depositing energy becomes a little bit more complicated. But there's a lot of work now trying to really understand this late emission. So the LIGO rate from one event is about 25 mergers per mega year. Remember, we talked about this 10 to the minus 5. That's more or less what LIGO sees. The estimates that we made with thermalization included, gives you a mass of about 0.06. And if you multiply those two rates, you get, again, the magical number of about 10,000 solar masses per year. So 10 to the minus 7 solar mass per year multiplied by the age of the universe 10 to the 10, we get about 10,000 solar masses of our process. So in principle, neutron star mergers can produce the total our process content. More importantly, when we compare what we saw with the predictions of the model, I mean, we need a model early on that basically doesn't have lanthanide, so with little opacity. But later on, we have a model in which we are absolutely sure that the second and third peak had to be produced because of the optical depth into the infrared. So we are basically sure the lanthanides have to be produced in order to make this spectrum. And now, if you believe my argument that in the universe, we know that the second and third peak are incredibly robust, then that gives credence to this idea that neutron star mergers could, in principle, produce the majority of the R process. And there's significant amount of debate right now thinking about whether or not they can do it early on in the age of the universe. Sorry, my kids are... Carlo! ¿Puede cerrar la puerta? Okay, so there is now some open discussion about whether or not these tidal tails that I talked about can actually produce the vast majority of mass. There's some argument that maybe when the two neutron stars come together, it's called the squeeze polar ejecta, where material is actually ejected so quickly that you can only, that you may only produce the first peak. Maybe the first initial peak came from that. And then the other component is maybe you have to wait until the merge system collapses into a black hole, and the accretion disk is the one that produces the R process. So a lot of open questions about this. This is the model that we put forward when we saw the observations. We said, well, there has to be, oops, it's a movie. It has to be a blue component, maybe the polar squeeze material, and then you need the red component, which have lanthanide. And amazingly, these models that were produced in advance of the discovery, give a relatively good prediction of both the bolometric and the spectral, which is, I think, a great achievement in the field. So I'll stop there. There's, of course, a lot of discussion, and Fabio, Diego, and others have been working really hard in thinking about, the jet emission of the system. You produce a jet or not. The neutron star mergers produce all heavy elements, are the sources of all our process elements. It's every single neutron star merger the same or not. Did this object collapse to a black hole or not? So I'll stop there and I'll take questions. Y muchas gracias.
Muchísimas gracias, Enrico. Creo que la charla fue maravillosa. Entonces, bueno, empezamos las preguntas. Enrique, por favor.
Hola, ¿qué tal, Enrico? ¿Me oyen?
Te oigo muy bien y te veo. Un placer.
Ah, perfecto. Pues muchas gracias. Muy buena plática, muy clarito todo. Pregunta. Hay este paper de Siegel, Barnes y Metzger 18 que argumentan que puedes también generar todas las condiciones. O digamos, creo que es la primera simulación que encuentra que esto se puede hacer también en colapsar. Supongo que es alguna en mil que te referías hace rato con supernovas, pero a fin de cuentas estos son pues, las hipernovas o GRBs largos o como les quieras llamar, todo junto. Que supongo que te da chocolate chip cookie y el otro es homogéneo. ¿Qué argumentos tienes para decir me parece que es más bien un merger y no un colapsar lo que te está dando esto? Porque siempre ellos dicen que la 170817 apunta que más bien son los
Enrique,
colapsos.
¿puedes quitar tu video? Porque se oye muy entrecortado. A ver.
¿Se entendió suficiente o lo repito?
Sí, entonces la pregunta es que hay modelos donde es un colapso de estrellas masivas que quizás pasa no muy comúnmente como para darte un GRB, que una vez que se colapsa en el disco de acreción se dan las condiciones necesarias para producir este proceso R. ¿Y qué pienso? Entonces, sí, digamos, lo que yo critiqué de ese modelo, tiene menos que ver con lo del disco de acreción, sino más con la idea de que estos colapsares también producen un montón de hierro, ¿no? Como tú sabes, los GRBs a veces vienen con supernovas tipo 1Bc y producen un montón de hierro. Ahora, el hierro es producido y bueno, Fabio es experto en esto, ¿no? El hierro es producido en la interacción del jet con la estrella y particularmente con el oxígeno. De hecho, Fabio y yo tenemos experiencias un poco interesantes ahí donde vimos explosiones por las redes que usamos. Pero bueno, entonces, lo que nosotros decimos es que está ya demostrado por las observaciones de las estrellas que no puedes producir procesos R también con mucho hierro, ¿no? Entonces, esa combinación, digamos, yo me quejé un poco de que no puedes producir mucho hierro, pero obviamente, y eso tú lo sabes muy bien, Enrique, que hay muchos GRBs largos donde no se ve ningún tipo de supernova, ¿no? Entonces también produjeron muy poquito hierro. Entonces, yo diría que lo que se deduce es que en el universo temprano se necesita algo que produzca un montón de material de proceso R, pero que no esté correlacionado con elementos alfa, que no puedas producir helio, carbono, oxígeno o hierro, porque entonces, como están ya ligados esos dos, si quieres, la abundancia, que es el cociente de abundancias de estos, se queda igual y entonces no lo puedes diluir de manera efectiva. Pero sí, entonces, digamos, les quería platicar un poco, bueno, si esto les interesa, de las discusiones que había digamos, hace 15 años. Y era cuando la gente utiliza estos modelos de evolución química, utilizan esta cosa que se llama el closed box model, que asume que todos los metales se mezclan instantáneamente, ¿no? Entonces, si tú asumes eso, si tú tienes dos estrellas de neutrones y quieres que coalescan, se tardan al menos cientos de millones de años. Y en un modelo de caja cerrada, no sé si se le dice caja cerrada en castellano, ya una vez que llegas a cientos de millones de años, ya la abundancia del universo ya es muy alta como para poder contaminar a estas estrellas con procesos R, ¿no? Entonces, nosotros hemos hecho ahora simulaciones ya de 3 dimensiones y digamos, la idea que yo les quiero dar es que si tú agarras una galaxia como nuestra galaxia temprana y dices, bueno, ¿cuánto se tarda una onda de sonido en cruzar la galaxia? Pues es más o menos como más de cientos de millones de años, ¿no? Entonces quiere decir que cualquier proceso turbulento que pase subsónicamente se va a tardar al menos, no sé, miles de millones de años, ¿no? Entonces ahí el debate es si los procesos que dan lugar al mezclado son suficientemente rápidos o no para que cuando lleguen estas coalescencias puedas contaminar a estas estrellas de procesos R. Y bueno, entonces la gente está trabajando en intentar, digamos, hacer estos modelos del universo temprano y ver cuál de estos dos modelos es más efectivo. Pero en general yo diría que sí, que yo creo que ya hay un debate bastante fuerte donde sí hay muchos aspectos que las estrellas de neutrones, estas coalescencias, les cuesta un poco trabajo enriquecer. Entonces, sí, se necesita un poco más de investigación, pero el modelo de colapsa normal que produce un montón digamos, de helio, carbono, oxígeno o hierro en particular, sí, ese parece que no funciona, ¿no? Entonces, bueno, Fabio sabe que muy bien que si tú dejas que la estrella colapse y todo el oxígeno se cae, y después se genera el jet, ya no produces nada de hierro, ¿no? Entonces quizás hay algo interesante ahí de cómo colapsan estas estrellas para todavía tener un disco de acreción sin tener los procesos que te dan lugar a una supernova, ¿no? No sé si te quedó claro, Enrique.
Sí, sí, está bien, está muy bien, gracias.
Alan, por favor.
Hi, Enrico. I'm gonna betray my ignorance of galaxy formation here. You argued that, quite convincingly, that the range of abundance, our process abundance variations at low metallicity argued perhaps for those R process elements being produced in neutron star mergers. But you need a long delay between forming your binary neutron star and having your kilonova, a gigayear. Does that fit in with the time scale, the age of those very low metallicity stars?
Yes, I don't have my slides, but I can show you some slides of some of the models that we did with the cosmological era simulations and with our EPO, in which we show that you need at least a minimum timescale of 100 million years. If you have 100 million years, it seems like you have enough time to actually enrich the stars. And
that's a merging time of 100 million years.
Yeah, a minimum merging time of 100 million years. I mean, there's some debate, and I think the jury is out because a lot of the mixing depends on how you implement like feedback, and different individuals are getting different things. But the way that you can think about this is neutron star mergers also travel relatively far away from their places of birth. As when we look at short gamma ray burst, where they happen in the galaxy, they're relatively far away. So they're depositing their metals there, maybe in the halo. So that metal basically has to cool, come back to the disk and get incorporated. And of course, in the simulations that we ran, it seems that we can actually produce, there were some, both mixing prescriptions and feedback prescriptions that did give you enough stars at low metallicity that are actually enriched with our process. But I would say that the jury is out, and that is a big tension point that, different simulations, I mean, our simulations show that you could, other simulations have shown that you can't. One of the interesting things is that because these events happen very rarely, if you think about, I talked a bit about this cooling mass, no? So the cooling mass is like 10 to the 3, 10 to the 4 solar masses, but the resolution of the simulations, of the cosmological simulations, is like 10 to the 5 solar masses. So basically, they, when they inject a neutron star merger, they use a kernel of how they distribute the metals. And of course, if you mix very efficient within 10 to the 5, 10 to the 6 solar masses of gas, then you will never see the abundance variations. So ultimately, what you're asking me is like, do you believe the simulations when they don't have the resolution to actually see, the mixing time scale and the mixing process at those scales? And the answer is no one believes it, and it depends on how they inject those metals.
I think my question comes down to how old is the universe when those stars were formed, and do we believe very short collision timescales for neutron stars?
Yeah. Let me show you. Let me see if I can. I'm going to show you the results of the simulation. Let me see. This is in a different presentation. So if you hold on 1 minute, I'll show you something that may convince you that that there's hope. Okay. Perfect. There we go. Okay, I'm going to try to. I'm not sharing my screen. Yeah, this is an incredibly important question. So. Okay.
Okay.
Okay, so this is the result of the simulations that we did. So if you take, let me see, so I can give you. So we did the, these are done with the Earth simulations, which is basically aimed to produce something that looks like the Milky Way. We basically inject both mergers and core collapse supernovae. We assume that the mergers trace the stellar mass, while type 2 trace the star formation rate. And so let me show you this. So if you take the simulation and you treat it as a closed box model, which is basically I just take the average abundance of cold gas, I get this blue line.
Right.
This is a closed box model, from Matteucci with 100 megayear delay. And you can see that if you basically just take into account the total average abundance of cold gas, then there's no way that you can actually produce the stars. But when you look at the stars, we are producing in the simulations a lot of stars that are low metallicity with high RMS fluctuations. And the argument is because early on in the universe, the average abundance of cold gas is not representative of the dispersion, the RMS dispersion from place to place within the Milky Way, just because the mixing takes quite a bit of time. So in this simulation, we were successful in able to reproduce the stars. So this is basically our simulation with 100 megayear delay, and we get something that looks relatively okay. But in order to do that, we actually have to tune or mixing coefficient or tubular mixing coefficient to get the magnesium over iron. So we basically assume that whatever it's missing, supernova is missing, it's mixing neutron star mergers. But that gives you basically the debate about whether or not in the simulations you can actually produce. Now it's like, so the question is, are you really close to a closed box model, or you have enough dispersion in the elements from place to place within the Milky Way? And different simulations get slightly different answers.
Okay, thanks.
Diego, por favor.
Vale. No me veo. Bueno. So, prior to 1708,
Te oyes muy ruidoso, Diego.
what were we expect? Déjame quitar mi video. Better?
No.
Más o menos.
Ajá. A ver, habla.
Habla. So,
Ahora.
before 1708-17, what were we expecting with the kilonova models? Like, were we expecting it to be a few days before, like blue, then a few days after red, or were we expecting something else? Like, so what was 1708-17 spot on with the kilonova models that we were expecting, or did it turn out to be sort of an outlier, which we now take as the model to be?
Yeah. I mean, some people may claim that it just exactly as they predicted, but there was a lot of models. So I would say, I was certainly surprised, and I think many other people were surprised about the blue component. But in all credit, Brian Metzger said that could be the precursor. There's still significant amount of debate as to even that blue component. It may not even be necessarily powered by radioactive decay, and it can just be thermal in nature. And Fabio has been working on models like that from the Cocoon emission. I think I think the thing that is incredibly surprising, I think, for people, and especially like, William and I that have been looking at the tidal ejecta, is the amount of mass. Like the amount of mass seemed very, very high to be producing a tidal tail. So it seems to me that the fact that this thing was so bright and produced so much mass was unusual. So you can take that argument and say, is that unusual or not? So then you can basically look at the models, take the same kilonova that we observe and say, would have been observed, in association with other short gamma ray bursts. And the answer is that it is, in many cases, it's actually too bright. So in some ways, it doesn't seem to match the standard short gamma ray burst model. So it seems that it may likely be in the kind of high end of the luminosity function in terms of producing mass when you compare it with observations.
What do the models say? What is the opening angle of the blue component?
I mean, it's highly unconstrained. No, I mean, I would say that that it can be, and because it's not moving relativistically, so it's hard to tell if it's 10 degrees or it can be 60 or 70 degrees. Yeah, so people try to actually take polarization measurements too, but it was not bright enough to take polarization. That will give you a little bit more of an idea if a little bit about the geometry of the ejecta. But I mean, there's a lot of degeneracy in the models, and there's lots of free parameters that you can fit. So, but I still think that it's kind of amazing that particularly I think the prediction of the spectra that it seemed to work so well. I was really impressed.
Vale, thanks.
Joel, por favor.
Hola Enrico, para mí es un gustazo conocerte, no había tenido la oportunidad. And then I'm going to switch to English. So, bueno, puedo hacerlo en español, pero bueno, creo que hay una persona ahí que a lo mejor no me entienda. When I was working in my master's with Jorge Hirsch and Alejandro Frank, so we were working in models. So we were considering this basic idea of the nuclei being like a liquid drop, and then it was very simple and very exciting to get some data right. So, but I started to add the deformation, and when I was learning in my PhD, where I was working with Gabriel Martinez and Karl-Heinz Langanke, was that probably this transition between spherical and well-deformed nuclei could be the sort of the origin behind of this rare air peak. But as I want to tell the people, so I was away from the field for around 5 years. So I don't know if there is any new concern to this rare air peak. If this should be a confirmation that is due to this transition between spherical and well-deformed nuclei, or it has to be more with the fission rate. I don't know if you have anything to say about.
Yeah, so Joel makes a really important point about, we have this peak in between the second and third peak, which it doesn't seem at first sight to, coincide with a particular structure, nuclear structure. So some people have proposed that, when you look at the decays, that there's basically some curvature in the, as you transition from the two, as he was saying, from the spherical to the highly non-spherical. And that curvature in the transition could be basically give to a pile up at a particular mass number. So, and then the other model is basically that the fission fragments, for some reason, prefer to fission at that particular mass scale, and therefore you get a peak there. And I think the jury is still out in the both models. There's a new experiment in Michigan taking place that are trying to basically characterize the nuclear, that transition from spherical to non-spherical with data looking looking at these very high energy collisions of nuclei, and they're able to actually now have enough resolution in time so that they actually start trying to characterize these nuclei that are basically very short-lived. And Luke Roberts now, who was a grad student working with me, and William is now working on that, and he thinks that maybe in the next 5 years they're going to have enough data to actually basically rule out that model or say that it is indeed what is giving you the rare air peak. So that's a kind of, people are very excited about that.
Okay, so a second question, which is related with more with your work about the light curves. So so the data that you show us like 5 years after the merge, right? Or 4.5 days, sorry,
yes.
Days.
Close to the peak.
So yeah, so I want to know which will be the physical conditions around that stage in terms of temperature, in terms of density, just to get a clue about which nuclei could be relevant.
Yeah, so by the time you
theoretical calculation,
what is kind of beautiful is by the time you see the radiation, the densities are fairly low. I mean, the way that you can think about it is take about 10 to the minus 2 solar masses. Yeah. Spread it on a photosphere of about 1 AU, or 10 to the 13 centimeters. And that more or less gives you the average mass. No, so the densities are now very, very low, and the average temperature of the material is close to the optical UV, so 10 to the 5 Kelvin. No, and one of the reasons is, what this is actually quite interesting, is that it is my understanding, and I don't do these models, that when people are trying to understand the atomic structure, so there, of course, nuclei are important in the sense that they're providing the heating, but the atomic structure of these nuclei, as you basically transition from being basically hot to, basically from hydrogen being able to recombine. So at later stages, you're going to go below 13.6 eV, which is, of course, as you know, the energy of the electron in hydrogen. So people trying to understand the atomic structure and the oscillation strength and the probability of decay struggle to do these n-body quantum mechanical calculations at these very low densities, because the densities are very low, as you pointed out. So then you're looking at things that are, yes, they are significantly denser than the interstellar medium, but in terms of what you care of, high densities, they're not, no, because the neutron star, was a 10 to the 6 centimeters or something like that. By the time you see the radiation is 10 to the 13. So, that's many, many orders of magnitude. And so the expansion just basically drastically reduces the temperature. But that gives you a feeling of the conditions, no?
So in this sense, the nuclear structure properties are relevant just during the first seconds of after the merge, so to say.
When you look at the heating rate, there's a little blip at about a few seconds, and that's basically where a significant fraction of the nuclear interactions take place. Of course, we were talking a little bit about that the expansion rate is a few tens to hundreds of milliseconds, and after that, everything is frozen, and you're basically expanding, and the only thing that matters is just the decay products, no? And I think the uncertainty there on those networks is really the fission fragment distribution. When these things fragment, what is their distribution, and thinking about what are the products in terms of photons and particles that will heat up the material, no? And then people have different ways in which those particles basically get coupled to the material, no? So as you know, there's a big debate as to, even if you're producing photons and you're optically thin, so the photons can escape, maybe if you have a magnetic field, some of the energy of the particles can still stay and things like that. So there's a significant amount of debate of the late heating trapping, but all of that it's basically more in the atomic physics realm than in the nuclear physics, no? Once you know the
Muchas gracias.
No, de nada.